So section 10.1 is all about this new thing R, our linear correlation coefficient. Of course, R estimates rho. This is the population parameter. That's your Greek letter here, the new Greek letter for today. And then we've got R over here. So Greek letter R, yeah, I guess so. And then R over here. R talks about the strength of a linear relationship between two variables. And I'll point out to begin with that R is between -1 and 1. So let's just make that pretty abundantly clear. -1 is less than or equal to R, less than or equal to 1. Now when R equals -1, that's a perfect negative relationship, perfect negative linear relationship. So I'll put that here. These two correspond with each other. So the nice thing about a perfect linear relationship is that when you know the value of x, you also know exactly what the value of y is. On the other end of the spectrum here from that, R could equal 1, and that's this over here. What you should notice about these two extremes is that they're perfect linear relationships. All this data falls exactly on a straight line. Now, if it doesn't quite fall on a straight line, but it still has a negative slope here, or at least approximately a negative slope to the data, then you're going to get a value close to -1, but not exactly -1. And likewise over here in the positive direction. But what about this? This is kind of like a jumble of data. Is there much going on here? Is there much of a relationship, a linear relationship between x and y? No. So this value of R, even though it's calculated at 0.08, really it's close to what value? What would you guess?
0.
Yeah, it's close to 0. Knowing the value of x here really tells you nothing about the value of y. So there's no linear relationship there. How about this last one here, F? I'm going to ask this question in a couple parts. First of all, is there a relationship between the x and y in this case? Nate's nodding yes. Oz is saying no. Who's right? Ah, you hit the nail right on the head. There is a relationship, but it's not linear. It's not a line. And that's what the linear correlation coefficient is all about. How much of a linear relationship in here there is. That's why you're getting 0 here. There's no linear relationship. It doesn't say that there's no relationship. It just says there's no linear relationship. So in a way, you're both right. But the big thing to understand is that R measures the strength of a linear relationship. Okay. So let's see what kind of hypothesis test we're going to do for this. So overall, when you're doing hypothesis tests in this section, we're going to test H naught such that rho is equal to 0 versus rho is not equal to 0. And it's going to be a little bit hard to get used to. But rho not equal to 0 says there's no correlation. No correlation. There's no relationship here at all. And then rho not equal to 0 says there is a correlation. That is, there is some kind of linear relationship between one and the other one. And that's all it says. That's as far as we can go right now. We'll learn a little bit more in conjunction with this on Thursday. But let's start here. Lemons and car crashes. The data are weights in metric tons of lemons imported from Mexico and U.S. car fatality rates per 100,000 based on some data from here. Is there sufficient evidence to conclude there's a linear relationship between weights of lemon imports from Mexico and U.S. car fatality rates? All right, so let me just highlight that, because this is going to be the source of our null hypothesis or our alternative hypothesis. And this one's a little bit tricky. There is a follow-up question. We'll get to that in a minute. We'll see about setting up an HO and HA. So the first thing is HO and HA. We'll kind of keep it on the simple side, rho equals 0 versus rho not equal 0. But which one of these do you think is our original claim? It's not exactly clear here. So I'll certainly have a little sympathy for people who disagree with me, and I'll be flexible about how I grade your wording of the conclusion. Now I got to vote for H naught, but if there is a linear correlation, what hypothesis does that fall in? HO or HA? HA. So it feels to me like this is our original claim. I mean, you can disagree with that. It's not, as they say, it's not a hill I'm going to die on. And I can grade your exam based on how you answered this part, which one was the original claim. Do we have a value of alpha here? No. So what value of alpha should we choose? Yeah, 0.05. It doesn't seem like the consequences of getting this wrong are all that heavy that we need to go to 0.01. So that's good. Step 3, this data should be in a data set that's linked off a D2L. So if you want to open that up, please do. So here's our data. No, that's the wrong one. That's data set 10. Here we go. 10.1. Example A. Let's copy this data and paste it into StatDisk. There's data that's already there, so just clear it out. By the way, an important thing about StatDisk. StatDisk doesn't like commas. One of your data sets has commas in it for like numbers that are bigger than 1,000. So if you have like 12,000 and it's written with a comma, you got to get rid of those commas before you do the analysis. So we've input our data, but now what? We haven't done this before. Where are we going to go? Where would you? Analysis seems like a good place to start.
Correlation and regression.
Oh, there you go. Correlation and regression. So hopefully pretty easy to find there for you. We've got columns 1 and 2 for our data. We're all set with our significance level, 0.05. Before I take a look at this, let's actually take a look at the plot. Does there seem like there should be a linear correlation between the two things? Do those dots look reasonably close to a straight line pattern? Yeah, this seems like it's pretty close. Doesn't seem like it's really random like example C from our handout just a minute ago. When we look at the results confirm your suspicion. What do I need at this point? Yeah, what's our p-value? 0.00992. So it really probably didn't matter if we chose alpha as 0.01 or 0.05. You're going to be rejecting either way. And that's our step 5. Reject H naught. Please put the H naught in there. If you just reject, sometimes they get a little uneasy. Are you rejecting H naught? Or are you rejecting HA? Let's see about stating our conclusion. give yourself a moment up there. Remember that our original claim was in the alternative hypothesis. So see what you can come up with. Which one of these are you going to put A, B, C, or D? Which one is going to be the model for you in wording your conclusion? All right, Oz, I think you came up with the correct one, so go ahead. Which one of these, A, B, C, or D? Matilda, she sounded a little less confident just now. It's C? Okay. All right. All right. All right. So the sample data support the claim. And now we're going to turn over to the problem itself. That there is a linear correlation between weights of lemon imports from Mexico and U.S. car fatality rates. So that there is a correlation, a linear correlation between the weights of lemon imports from Mexico and U.S. car fatality rates. Nice, nice. There we go. Are we okay with our conclusion? Lisa?
Yeah, I was wondering why it wasn't, A, because I thought we did not have an equality there.
So it's a little tricky. To me, this feels more like we're testing this claim as our original claim. But if you wrote this one, you could easily write your conclusion based on this being your null hypothesis and that you rejected that. So if you wrote, or if you decided this was your null hypothesis, then you could word your conclusion this way. There is sufficient evidence to warrant rejection of the claim that there's no linear relationship between the weights of lemon imports from Mexico and U.S. car fatality rates. So basically, you'd be doing more or less the same thing, except that you'd have to say that there's no linear relationship here as what you're rejecting. You're saying that that's false, and if you're rejecting that, that means that there is a linear relationship. So you could still word this in the correct way. You just have to be careful. To me, it feels more like this. I can't say I feel really strongly about one versus the other. I'm sympathetic to the desire to say that that's H0. All right, but use the wording, the conclusion, either way, and you should be able to come up with something that works here for us.
Okay, I have a question.
Yes.
So
Yeah.
if you said that if HO is rho equals L, then there's no correlation.
There's no correlation. Yeah.
For HA, if rho doesn't equal L, then there is a correlation. So how would someone say that it would be HO?
Well, the conclusion is that you're rejecting HO, and if you're rejecting HO, you're rejecting the fact that there's no correlation between these imports and the fatality rates. That would be the conclusion that you'd be rejecting. Feels a little harder to do that because you're going to have to kind of put in the words no correlation into this sentence. But if you thought that this was your original claim, you would word your conclusion based on that. So your original claim contains a condition of equality. Did you reject it? Yes. And you state there's sufficient evidence to warrant rejection of the claim that, and now we got to put our original claim in words. The original claim here would be that there's no correlation between these two things. between these lemon imports and fatality rates. So that would be the conclusion that you're rejecting. So it's different. I mean, you can still get this. You're still getting at the same thing, and that is, we think this is what the case is. There's a follow-up question to this, and for that, let me look back at the graph. So the graph looks pretty nice. The follow-up question is, do the results suggest that imported lemons cause car crashes? So my son always uses this one against me, and it just grinds me because I know he picked it up in the stat class. Correlation is not causation. Just because something's correlated doesn't necessarily mean that one causes the other. We've got a world of data out there, just tons and tons of data. And just because something happens to be correlated doesn't mean that one causes the other. Now on Thursday, we're going to spend some time deciding, well, what does it take to establish that there's a causal relationship between two things? At what point do we say, yes, cigarette smoking causes cancer? That kind of thing. That's going to be a little bit more than we can discuss here. But right now, I mean, the cute one or couple words summary is that correlation is not causation. So the answer here is a big no. All right, let's move on. Example B. So moving on down. This is kind of nice because it's a non-invasive way to get some of these weights. Listed below are overhead widths. It says in centimeters. That feels off somehow, unless they're talking about maybe the heads. Even then, it seems pretty narrow. Of seals measured from photographs and the weights in kilograms of the seals. The purpose of the study was to determine if weights of seals could be determined from overhead photographs. Is there sufficient evidence to conclude that there's a linear correlation between overhead widths of seals in photographs and the weights of seals? So, okay, let's take a look at that. Sufficient evidence to conclude there's a linear relationship between the overhead weights of seals or overall widths of seals from photographs and the weights of those seals. So let's pick up our data from example set B. Let me pull that up. Here's example B. Paste it into our data set. Let's clear out the old stuff. And to get started, let's talk about what our null and alternative hypothesis. So let's go down to this. Again, this is one that feels kind of tough. It's like, well, really, I'm not sure. So example B. So once again, we're going to have rho equals 0 and rho not equal to 0. But the question is, what's your null hypothesis? Let's look back here at, no, wrong one. Let's look back here at the problem itself. We want to test that there is a linear correlation between the overhead widths of seals from photographs and the weights of the seals. So is that HA? Yeah, I'm feeling more comfortable with this one. Feels more like HA. So there's our original claim. Did they give us alpha in this one? No. So what should we use? 0.05 seems pretty good. let's input the data. Done. I need a p-value here. Yeah, that sounds pretty good. Is everyone able to get 0.020, p-value. Let me see some nods. Are you guys able to get that p-value? Okay. All right. Jackson, what does that p-value tell us to do with our null hypothesis? Nice, thank you. Reject H naught. And now let's state our conclusion in words. So going back to our little handout here, which one of these A, B, C, or D are we going to use? C, yes. Sample data support the claim that there's a linear correlation between, and then let's go back and take a look at the rest of this from our handout, that there's a linear correlation between the overhead widths of seals from photographs and the weights of those seals. So looking pretty good there. Sample data support the claim that there is a linear relationship between the widths of seals from photographs and the weights of seals. All right. I'm missing something here. Correlation is not causation. Yeah. How did that get by me? My bad. It's just a bad day. All right. Correlation is not causation. Correlation does not equal causation. We'll talk more about that Thursday. You okay?
Yeah, my sister had to go.
Okay. Good luck. Take care of family. All right. One thing that I want to share with you, something that might come up with, or might come up in your homework, something that's not really a big deal for me, is that you might need to actually find the test statistic. So if we go back here and look at the current data set, I never actually did run through the analysis myself, but you guys did come up with the right numbers. Columns 1 and columns 2. So you get a lot of output here. Now the one thing that you don't get is the actual test statistic. The test statistic is how they determine the p-value. In this case, it's a t-distribution with n minus 2 degrees of freedom. So let me go to this page right here. That's how you would actually do the test statistic. So that's what StatDisk is doing, is it's calculating this. It's going to get R from your output and take R divided by this square root term, where n is the number of data items in your data set. So n minus 2 is really degrees of freedom. But let's write this down so that you have it. Because somebody's going to be hitting that, ask your professor button. And I'm going to say, look at your notes. All right. Your test statistic is based on this. R over 1 minus R squared over n minus 2. That's your test stat. And that's for a t-distribution. And depending, well, in this case, it's going to be a two-tailed test, but you could find a p-value based on your t-value, etc. I think they might just ask you for the t-value itself. It's not a test question for me. I'm happier that you're able to do the rest of this stuff. Find the p-value, decide to correctly reject H0 or fail to reject H0, and then word your conclusion in words. But just so that you have it, in case you need it, there it is. All right, comments or thoughts on example B? We're going to skip example C for now. We're going to see some of the CODAP on Thursday. What do you need?
Can't see that. Gracias.
Let's move on to example D. So what we've got here is two different data sets. They're really, if you take a look at the Y values, they're the same in both cases. You got Y1 here and Y2 here. These are the same values. And what it reflects is different distances and how long it would take somebody to run those distances. So the difference between the two data sets is that the first one is in miles and the second one is in kilometers. Let's see how changing units affects the actual value of R, or if it does affect it. Maybe it doesn't. Let's find out. We'll experiment. Let's experiment with some data and see what happens. So I labeled it example C. I guess it should really be example D. But let's start out with this data set. Paste that into StatDisk. So there. And then while I'm at it with the data, I'm going to go down and collect this one as well. And I'm just going to put that in columns 3 and 4. Even though columns 2 and 4 are duplicates, I still got them in two different columns. Let's find the value of R for this first two columns. Is there a relationship between how long it takes somebody to run these various distances? We can kind of hint at it, I suppose, if I were to look at it in an exploratory way, but let's just go to the analysis. I think we can see the same thing from there. Correlation and regression. I'm not going to worry about 5% level or 1% level here because I'm not doing a formal test. What I want to see is I want to see the value of R. Now take a look at this plot. What do you think the value of R would be close to? Yeah, it's close to 1. I mean, this is fantastically linear data. So that's kind of a nice relationship there. Let's look back at the actual results. If we were doing a hypothesis test, do you suppose we would reject H0 of rho equals 0 or fail to reject H0 rho equals 0? What do you think we'd decide here? Yeah, you'd be rejecting. Is it even close? No. That's really convincing evidence. A p-value is 0. But what I wanted to see here is the value of R, and that's amazingly close to 1. So we get R equals 0.99927. What if I change things up, though? What if I look at the value of R for this data set? Do you think we're going to see a change or no? Let's find out.
Yeah.
We'll find out by experiment. So we'll go back to analysis, correlation, and regression. This time, actually, I guess I could have just changed the columns, 3 and 4. Didn't have to do all that. I know. Matilda thinks I'm funny. Did it change the correlation coefficient at all? No. You get the same thing both ways. R is 0.99927. Okay, well that makes sense it's still more or less the same data. You've just changed units. Changing units does not change the correlation. So looking good on that one. The plot still looks more or less the same. You've got some values that are tightly clustered around this line. On Thursday, what we're going to do is we're going to try and find out things about this line, its slope, its y-intercept, etc. But that's for Thursday. For now, how are you looking with this one, the changing of the units? All right. Let's work through example E. See what's going on there. 20 different statistics students are randomly selected. For each of them, their body temperature in degrees Celsius is measured and their head circumference is measured. For this sample of paired data, what does R represent and what does rho represent? Good questions, good questions. Think about that for a second. What does R represent? What does rho represent? But what does R represent in here?
Correlation between body temp and circumference.
Okay, correlation between body temperature and circumference. There's one thing, I mean, I could say the same thing about rho here, right? Correlation. Close, not test, but this is your sample statistic. What's this? Ah, well done. Thank you, Sam. Population parameter. So we measure R from our data, and we hope that it's a good estimate of rho. We're going to use R to make test of a hypothesis about rho. Okay. Without doing any research or calculation, estimate the value of R. What value of R do you expect? This is a good one. It's really asking, do you understand really what R is all about? I'll give you a moment on that one. Talk to a friend, talk to a neighbor. What do you think the value of R is? Talk, not giggle. Keep in mind some of your choices here. So do we have a consensus? What do you think the value of R is going to be? A 1? Does it make sense that as somebody's head gets bigger, their body temperature goes up? Or is it the other way around, that their head gets bigger and their body temperature goes down? Do either of those make sense? What do you expect? I'm thinking approximately 0, right? That there's really no linear relationship between these two things at all. That, you know, some people have bigger heads than other ones, smaller heads, but that's not really going to correlate much to body temperature in degrees Celsius. Yay. All right, C should be easy. Does R change if body temperature is converted to Fahrenheit degrees? No. We just saw that one up above. So, no, it's not going to change with degrees. Now, only one of these statements below is correct. Question is, which one of them? And maybe you can help me work out part of it with this first one. D here. When I say first one, I mean first one I'm going to look at. What's wrong with this right here? It's a statistic. R is a statistic. It estimates rho, but it's not a parameter. So we can get rid of that one. So now you've at least got a 1 in 3 chance if you're just outright guessing. So they've improved our odds a little bit. Like 8% maybe, I guess. Close enough.
What's your answer?
I like that. It's cool.
See, that's what you need to start doing. Call the person out first, then estimate.
Oh my gosh.
We answer it and be like, question, everybody answer.
Oh,
What
Sam,
time?
what do you think?
Like, don't throw it.
I think it was right.
So there's a lot going on here, but one of the things that R doesn't describe is the proportion of variation in the head circumference. It's explained with the variation in body temperatures. That's going to be something else. We'll see more about that next time, but that's not really what R is doing. So I'll get rid of that one. And in the same way, example C talks about the statistic representing the proportion of variation in the head circumference, etc. Again, that's not what R is talking about. R talks about the linear correlation coefficient from sample data, and this is the linear correlation coefficient for the population. So example C, or example B here, answer B, is the winner. We will learn what it is that talks about the proportion of variation that's explained in terms of, X explains Y, or the horizontal axis explains the vertical axis. But are we okay with our conclusions for example E? All right. We will play around with that CODAP from example C next time. But let's call it a day on this one.